So today we're going to do something that's pretty conceptually important and which you should really understand well, which you might have seen earlier, but you should understand well, which is the LZ reduction formula. So okay. So last time, we had this description of the S matrix, and the way we wrote the S matrix was, let me just get the notation right. We define this object which we call phi f of t, and this was I integral phi h x t. And this is integrated over d3x. So this is the Klein-Gordon inner product of the field. This is the solution of the free wave equation. And this is the Heisenberg field. This is the field operator. Okay. And what we showed was that this now our notation is slightly unfortunate because this we call this is what was a creation operator, right? So we showed that if you looked at k phi f of t 0, this is f of k, independent of time, okay, and on the other hand, if you looked at multi-particle states, this phi f could create them, but it did not create them in the limit the time went to infinity. Okay, so let's say we want to look at the 4-particle state. Then the idea was, I think this is where we stopped last time. We look at so the idea was that if you want to define the S matrix, then you can define in states by basically acting with one of these guys, but acting in the far past. Okay, why do you have to act in the far past? Because when you act in the far past, you see this is not really a 1-particle creation operator. Right? This actually can create also multi-particle states. However, when you go to the far past or the far future, this kind of operator, the contribution of the multi-particle states goes away. Okay. Therefore, also, in general, you have 2 operators. You might worry about what kind of ordering you have to take, but in what we'll discuss, we'll always take these f1 and f2 to correspond to plane wave states which don't have overlap in the past. Okay, so they're not the same momentum. If you do that, it doesn't matter what ordering you take, whether you put t1 to the right or t1 to the left here. Okay, and so you go to the very far past and you act with 2 of these guys, that creates a 2-particle state. You go to the very far future, you act with 2 of these guys, it creates a 2-particles out state. Okay? And so this is in out. Okay? You see our notation is slightly unfortunate because we've denoted creation operators this way, and we've denoted annihilation operators with a dagger, okay, which is kind of the opposite of what we had. But that's because of the way we defined this. Okay, we started by defining this, and we wanted this kind of property to happen. Okay, so even in these, f3 of k is just a positive frequency solution of the Klein-Gordon equation, so it satisfies this. Right? The question of whether it satisfies this or not is a question of what kind of frequencies you put in f. Okay? Whether you take f to be only positive frequency or only negative frequency. Okay, so we made a choice last time, and with that choice, these Hermitian conjugates act like annihilation operators, and those things act like creation operators. We're never going to consider the commutation relations of these guys. It's just a question of which creates states on the right and which creates states on the left. Okay. 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 Is this clear? Is this definition of the S matrix clear? Yeah. Okay. So the LSZ reduction formula. Now this is fine as it stands. However, and in fact, you could just start by trying to use this. However, the problem with this is that it's not very clear how to do perturbation theory with this. Fine, this is a good definition of the S matrix, but how should I do perturbation theory with this? How do I compute this in perturbation theory? So you could say, well, compute these things as functions of time and then take time to infinity, and that's okay. One way to do it, which we could do, we could try and compute these Green's functions as functions of time and take time to infinity. But that's not a very easy thing to do, and therefore the LSZ reduction formula gives you a more convenient way to do the same computation. Okay, and the LSZ reduction formula is that if you want to compute this guy, so this is F3, F4. Out. And it's important, I want to state again that it's important that F3 and F4 don't have overlap in the far past. So you could say that we are computing S minus 1 if you like, in that we are not looking at the delta function term. Okay, good. So the proposal is that this object can be written in a different form, and this is the LSZ reduction formula that I'm now stating, and we'll prove. I'm stating it for a 4-particle state, but obviously, there's nothing special about 4 particles. This formula I'm writing is going to work for all particles. These are the same wave packets that appeared here. Okay. However, notice that F3 has been conjugated, F4 has been conjugated. Okay, and then you have product over J box J plus M squared I, and then you have this thing acts on the following operator. Okay. Okay. So just look at what this formula is saying, right? It's saying we compute this Green's function. This is the quantity we've discussed. This is the quantity we also showed how you could compute in perturbation theory. I said was intrinsically of interest. And there are 2 things you could do. Well, you could integrate it with time. You could do this integral and then push these points off, some of the points off to plus infinity and some of the points off to minus infinity. And that's a good way to compute the S matrix. That's in fact the definition of the S matrix. Okay. However, there's something else you can do, which is take this guy, act on it with this box plus M squared. Okay. Box plus M squared, this is a product over J. That means you have box 1 plus M square, box 2 plus M square, box 3 plus M square, box 4 plus M square. So J runs here. There's a factor of I here. So J runs here from 1 to 4. Okay. Do that. Take the answer, whatever you get, it's some function of x1, x2, x3, x4, and integrate it with these functions. Okay. And the claim is that this gives you the same answer that you would have got by pushing these things off to infinity. Okay. Okay. Is the proposal clear? Okay. So now, when you look at this for the first time, it might seem that this is a mysterious proposal. How is this? What does this mean? However, if you think about it in momentum space, you'll see that it's not that mysterious. Because what is this in momentum space, right? This box J plus M square. This box J plus M square in momentum space, in the end, is just K squared plus M minus M squared. Okay. So in momentum space, There's a minus sign, and once you include the i's, you'll find this. Okay. So see what this is telling us to do. What this is telling us to do is compute this quantity in momentum space. Okay. It will have some external propagators that are sticking out, right? Remember what we were saying last time, right? It will have some external propagators that are sticking out. This thing multiplies things with k square minus m squared by I. Okay. Now in the free theory, that would exactly cancel out the propagator. In the interacting theory, this doesn't exactly cancel out the propagator. Okay. However, after that, do an integral with these solutions of this Klein-Gordon equation. These solutions of the Klein-Gordon equation only have momenta that satisfy k squared is equal to m squared. Okay. So, you are in the end, it's as if you're computing this in momentum space. Okay. Then you strip off this factor and then you put the momenta on shell. Now you might have said, if I strip off this factor and I put the momenta on shell, I'll get 0. Okay. You would have got 0, except that Green's function has a pole at this value. Okay. And this procedure is basically just telling you to pick out the residue of the pole. Okay. So this is saying, in words, S matrix is the residue of the pole in the Green's function okay. Here we've taken all the particles to have the same mass. However, if you like, you could give them different masses. Okay. Okay. So the LAZ reduction formula is telling you that this S matrix is actually the residue of the pole in the correlator at k equal to m squared. Okay. Okay. Is that clear? Okay. So now we have to prove the LAZ reduction formula, and I'll proceed to do that. Are there any questions about this so far? Or? Okay. Okay. So first I want to prove an intermediate result, which looks at the quantities that appear there. You see, the quantities that appear here are this box plus m squared times del h, okay, where this is some solution of the Klein-Gordon equation. So first I want to prove some intermediate algebraic result. This is the kind of quantity that's appearing there. It's appearing 4 times. Right? You see, it's the product of 4 quantities of this kind. Okay. Okay. So this quantity looks like okay. This d squared acting on f of x. Okay. You can move this d squared acting on this f of x to be on the left hand side. So this looks like I, okay, f of x times d0 squared by h of x, okay, minus or plus m squared f of x by h of x minus d squared f of x by h of x. Why am I allowed to do this? Well, I'm allowed to do this because this f of x we're assuming is some wave packet, and it's a wave packet that has finite extent. Okay. Because it has finite extent, it doesn't have any support at infinity, and so there's no boundary term when you do this integral. Okay. And you can just shift the del squared from acting on f of x to acting on phi of x to acting on f of x. Is this clear? Okay, good. However, what do we know about f of x, right? What we know is that f of x satisfies d0 squared minus del squared plus m squared f of x is equal to 0, right? Because solution of the Klein-Gordon equation. It's a sum of solutions, but it's a linear equation. So it's a solution. Therefore, minus d squared of f of x is just so instead of having minus d squared f of x, I could just substitute minus m squared f of x minus d0 squared f of x. Okay. Now notice if you put minus m squared f of x here, that cancels off this m squared. There's another term that remains. So this looks like I times f of x d0 squared phi h of x minus d0 squared f of x times phi h of x. Okay. 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 But this thing, in fact, is a time derivative. Okay. So you can think of this as I times integral d0 times f of x d0 phi h of x minus f of x phi h of x. In fact, this I can integrate over d3x, and then I can do, I'm just splitting the integral into two parts, right? Okay, but now it's the integral of a time derivative from overall space. So this integral almost cancels that out. You might have thought you get 0, but you don't get 0 because in this case you do get a boundary term. And let me just get my signs right. And this boundary term looks like phi f of minus infinity minus phi f of infinity. Because this quantity that we've defined, actually we can check with what we had above. Yeah. You see, this quantity that we have defined is just minus phi f based on how we defined it there. It's minus phi f because we chose to define phi f as phi times d0 minus d0 phi times f. Here we have f times d0 minus d0 f times phi. Okay. So it's just minus phi. Okay. And therefore, you would have got phi f of plus infinity minus phi f of minus infinity by doing this, but because of minus sign, you get this. Okay. Okay. So that's the first result. Is this result clear? Yeah. So this integral, okay, gives you difference of okay, that's what we just proved. I mean, there's some set of equations, but what we've proved is this. Okay. So is this clear here? Okay. Even if some of you have seen this before, this derivation is quite a tricky derivation. It's conceptually important. So it'll help if if you think about this, if you have questions, if you ask. Even though it might all seem very simple, if you go back and think of how to derive this, you'll find that this is a conceptually subtle derivation. So, but do think about this. Okay, good. So we have a similar result, of course, for f star x, and that is that I into f star x into box plus m squared. Okay. This looks like phi f dagger infinity minus phi f dagger minus infinity. The reason you get the different sign is because of the dagger. Okay, the dagger also flips the sign of I. So in this case, you get infinity minus minus infinity. In the other case, you get minus infinity minus infinity. Okay, remember this actually is what we are calling an annihilation operator, even though it looks like a dagger. Okay. Okay, are these results clear? Okay, very good. Now, I want to consider the case where, as we've been saying many times, you know, these F1, F2, F3, F4 are orthogonal to each other. Okay. So we are going to actually, now using this result, let me leave this line here and erase the top. Now there's a slightly subtle step. Okay. The subtle step is that we have a time ordering here. Okay, and the time ordering is actually important. The time ordering is not unimportant. But you know, we are going to take this box plus m squared and move it into the time ordering. That's a slightly tricky step because you know the box in fact has a d0 squared and the time ordering has various theta functions. Okay. So when you move the box into the time ordering, you might worry that you know you get some derivatives of theta functions. Those derivatives, you remember the time ordering, the difference between one time ordering and the other time ordering is always just a commutator, right? And the commutator always vanishes unless you know you're bang on top of each other. So the difference between you know one time ordering and the other time ordering always has to give you something that looks like a delta 4 of x1 minus x2. So you see, you know, there'll be some terms that you will get from the box acting on these t's, but those terms will basically end up just contracting these f1s and f2s or f1s and f3s and so on. So you can argue that in this limit, it's okay in this limit where these wave packets are you know orthogonal to each other to move the time ordering into the, to move the derivatives into the time ordering, okay, so that you have box plus m squared sitting inside here rather than outside. Okay. Okay. If you do that, then see what happens, right? For what? Which creation? Here? These are functions. There's no time ordering here. Time ordering only makes sense for operators which don't commute. These are just some complex number functions. So f is just a function. It's like e to the I kx with f of k. Here, there is a time ordering. Sorry, what? Phi. You mean what I had written here? So there was a time ordering there because the things, the creation operators were all acting to the left, and the annihilation operators were all acting to the left, and the creation operators were all acting to the right. So there was an ordering. I mean, x1 and x2. Sorry. What doesn't matter? I mean the time ordering. That here we x1, x2, x3. Yes, we have to time order the correlator. Yes. In the last case. In which last case? When we are writing phi f, those operators. No, phi f. There was a time. You see, what we said was that. It said something like this. I have put a time ordering here. I've already put it here. Yeah, the T1, T2 ordering doesn't matter, but this mat. Here I've put an ordering. Look, later is to the left. These are the later operators there to the left. If you wrote this formula with these guys to the right, it wouldn't work. Okay. So the later operators are to the, sorry, this had a dagger, yeah. Okay. So these operators are to the left, those operators are to the right. So later is to the right. There was some issue of what about the relative ordering of T1 and T2? That's an, you could have asked a question about order of limits issues. Is it the case that T1 is always larger than T2? Or what if I take, T1 to be smaller? Like, do I have to take the limit T1 to minus infinity first or T2 to minus infinity first? There's an order of limits issue, but that order of limits issue doesn't matter because, these operators at T1 and T2 are going to commute because F1 and F2 are widely separated. Sorry, this is all, yeah. Because F1 and F2 are widely separated, so these operators are going to commute in the far past. So it doesn't matter if you take this one first to minus infinity or this one or the other way around. Okay, that's because these operators commute in the far past. That's different from what I said here. Here, these operators xi's are not all in the far past. This is an integral over d4x. Here, the integral is only over minus infinity and plus infinity. Here, there isn't so much subtlety. This is, you've already taken the limits. You're just saying something is acting at minus infinity, something is acting at plus infinity. Here, the integral is over all of x, so you have to be more careful. Here, there's no integral over x. It's just a limit. Okay, is this clear? Okay, good. So, okay, so we are going to push this, this through a time ordering. So now, what will we get, right? What we will find will be the time ordered product. Okay, now look what will happen here. What we'll get here will be, let's say we allow ourselves to push the time ordering, okay, and then we use the formula that we had above, okay, which is hidden below. Okay, then what will happen is we'll get from here, and then we'll get the time ordered product, okay, of phi f1, okay, plus infinity. Sorry, this should be minus infinity, minus phi f1 plus infinity. So this expression becomes equal to phi f2 minus infinity minus phi f2 infinity phi f3 dagger plus infinity minus phi f3 dagger minus infinity 4 dagger. The whole thing is inside a time ordering, and then there's a vacuum. Do you see this? Yeah, I allowed myself to push this, to push these things through the time ordering, to push the derivatives. But in the end, the time ordering is still important. It's not like the time ordering is just completely unimportant. Okay? So you get the time ordered product of all of these guys. Is it clear how we went from there to here, or is it not clear? Clear or not clear? Clear to everyone that how we went from, yeah. Yeah, I said, you said about the theta functions, all I was saying was that, the result we derived was for f times the derivative of phi. However, what we have here is the derivative outside the time ordered product. Okay. So there is one part of this derivative that actually acts on the theta functions. Okay. That part which acts on the theta functions, once you combine it with the commutator, will become like a delta 4 of x1 minus x2. Because, what will it do? There's a d0 and there's a theta of x1 minus theta of x2, theta. So, you'll get some delta 4 of x1 minus x2. And that term will just end up setting two of these points to be the same and collapsing one of the integrals. But if you assume that these f1 and f2 are orthogonal, then that integral doesn't contribute. Therefore, I said that you could think of this as the time ordered product with the box inside rather than outside. Once I put the box inside, then I use the result I had previously that's hidden below that board. Okay. And then I converted this into this. So remember, when you integrate with f1, you get the creation operator at minus infinity minus the creation operator at plus infinity. Here you get the creation operator at minus infinity minus the creation operator at plus infinity. Okay. On the other hand, for f3, we have f3 star and f4 star. So that looks like the annihilation operator at infinity minus the annihilation operator at minus infinity. And similarly here. That's because we have stars here. Okay. Okay, good.
Although, won't we have like a double time derivative?
What?
So we'll have a double time derivative.
Yeah.
So it will be a time derivative of the theta function, so a delta function.
Yeah.
So wouldn't we require that f1 should be orthogonal with the time derivative?
No, you can, when you go through this, it's like the manipulation you do for the Green's function to show that box plus m squared on something gives you a delta function. So it's like, remember how this whole thing works also at the level of because and the reason that happens is because the phi's commute with each other. It's only the phi and the d0 phi that don't commute with each other. So you have to have one of the d0s acting on the phi and the other acting on the theta function, and so you'll get a delta 4 of x1 minus x2. Okay. That being said, this is a step which one could do more carefully. We are waving our hands a little bit. And we are imposing some conditions on the f's. But basically, the point is, provided you take the right kinds of f's, this kind of term is not important. This subtlety is not important. The fact that you will get a delta 4 is similar to deriving a Green's function. Yes, that's right.
Taking this one orthogonal is this strictly reasonable because there can be some momentum modes in the particle that coincides with the out particle.
Yeah, but it's reasonable, and we are making the assumption all the time. You see, that's why we are computing s minus 1. We are never computing the part where the in has some momenta which are the same as the out. That would give you a delta function, and we are never computing that. So the LSZ formula is always useful for computing s minus 1. Okay, and so it is reasonable, to assume that there's some forward scattering which you're not so interested in.
So
yeah.
So the left hand side is already s minus 1.
That's right. I mean, the left hand side is s minus 1. The left hand side is actually just out and in, but with when you assume that these f1, f2 are orthogonal to f3, f4, it is, the 1 gives you 0 in this case. So left hand side is in this case is s, but this formula is true provided you've made this assumption of orthogonality.
Yeah, the right RHS is just s.
Well, the this is an equation. In this case, this is s. Okay. This equation would not be true if some of the f1s, f2s, were not orthogonal. Okay. So if you wanted to compute the 1 in the, if you drop this assumption, then you would find, the LSZ formula becomes subtle if you try to look at forward scattering.
Can we track those if we don't take this as orthogonal?
You can, but I mean, the forward scattering is some triviality. It's a 1, right? So I mean, sure, you can. You don't need to do anything to track it. It's just a 1. It's some delta function. It's a disconnected part, so you know what the forward scattering is. I mean, 1 we don't need any perturbation theory to evaluate it. It's just 1. Yeah.
Why can't I use perturbation result?
What perturbation result?
Because we are shown as E of phi1, phi2 interaction times s.
You can use, but we will use it. But why do you want to use it right now? It had s. Oh, but that s. Sorry, that s is was our definition of e to the I h I dt. That's not what we want to compute. What we want to compute is this, right? What we had there was something that we were calling e to the I integral hi from minus infinity. That's not actually the S matrix that we want to compute. The S matrix you want, this is really the S matrix. Okay. We are using the symbol S for this guy. This can't be the S matrix. This is something which depends on what I called hi. let's say I choose to say HI is 0 or my whole Hamiltonian is H0. This is something which is useful in perturbation theory. It's not something that's intrinsic to the theory. Whenever you see interaction picture, you should see it's something that's useful in perturbation theory. Okay. Sometimes you can use perturbation theory to prove results about the theory itself, but this quantity is not really the S matrix. This is the S matrix. That's it. Yeah, where is the HI here? We never introduced any decomposition into H or HI or anything, right? This is the full Heisenberg operator. There's no H, HI, nothing, right? There's no H0, HI. This is not a perturbative result. In this case, there's no choice to make. That's right. This is really the S matrix. It's the overlap between two natural Hilbert spaces, one at minus infinity, one at plus infinity. Well, first we have to prove this formula. This formula is useful because it's useful perturbatively. The original formula is not so, actually you can do it perturbatively, but this formula kind of tells you how you should compute that quantity in perturbation theory, because it's useful to understand momentum spaces I wrote somewhere and erased, right? This is just k square plus m square. And then we know how to compute the right hand side. Okay, is this clear? Okay, now look at what the time ordering does, right? The time ordering, as I said, is important. It's important that's a time ordered product. Okay. What does the time ordering do? Well, the time ordering pushes all the plus infinities to the left and all the minus infinities to the right. So what do you get? There are many terms, right? Let's look at some terms which we get, which we like. Here's one term which actually is the term we want. Okay. This is one term which comes from there. Do you see? It came by picking up the f1 of minus infinity, which went to the right, the f2 of minus infinity, which went to the right, okay, the f3 of plus infinity, which went to the left, the f4 of plus infinity, which went to the left. Once again, I'm assuming that the order in which you take f3 and f4 to plus infinity doesn't matter. Okay? In fact, in any case, they're both annihilation operators, and so they commute as you go to infinity. But when you go to infinity, these wave packets are separated. So even if this had some component of a creation operator, this order of limits I'm not caring about. You see where this term comes from? This is actually the term that we want. It's the same term that we had before we erased. You see this? So this is actually the term that we want, but it's only one of the terms. In total, we have 16 terms here, because there's 2 to the power 4 terms. So it must be the case that all the other 15 terms are 0. Okay. Okay. Indeed, it's the case that all the other 15 terms are 0. Why? Right. Let's look at some other terms. Okay, plus 15 other terms. Okay, all of which are 0. Okay, I won't show it for all of them, but it should be pretty clear why they're 0. Okay, you see, let's look at this guy. Okay, and let's look at some case where let's write down. Okay, tell me some other term that we have here. Let's look at phi. Okay, you guys tell me which term should we look at? Okay, fine. So let's look at this, right? Phi f1 of infinity, okay, phi f2 of infinity. There's one term which is where you pick up the plus infinity parts from here, phi f2 of infinity and phi f1 of infinity, okay, and you pick up the minus infinity parts from the f3 and the f4, right? So phi f3 of infinity. However, remember that this is a creation operator. So it has only positive frequencies. Because it has only positive frequencies, it can't act on the vacuum. it acts on a vacuum, it gives you 0. You see? So this is a creation operator at plus infinity. But the creation operator at plus infinity, if it acts on the vacuum, it's going to give you 0. So you see, the point that we proved earlier was when you look at the algebra of these operators and you go all the way to infinity, then basically they create one particle states and they don't do anything else. Right? So they behave like free field operators. Not because they are free field operators. At a finite time, they create all sorts of things. But at plus infinity, they behave like free field operators. In fact, here we don't even need that logic because you see, this just is something which has, which is a creation operator. Remember, there's a difference in notation. In the usually we would have written this as a dagger. Okay? And so it acts on the left, it gives you 0. Okay? Similarly, on this side, this is an annihilation operator, acts on the vacuum, gives you 0. Annihilation. Wait, how would annihilation on? Tell me, yeah. What factors?
I mean, for taking time order,
Huh.
take the product of all possible terms. So there will be 16 or some.
There's 16 terms, yes, but the time ordering is very important.
Yeah, but now there will be 2 terms. It's like time ordering of 5 T, 5 4 doesn't matter. So that side I can change, but this side keeping same. F1, F2 says.
This side also you can change. At minus infinity, everything commutes.
4 terms.
Which 4 terms? Where are the 4 terms?
So before taking time ordering, I
Yes.
also have one term, the one which you wrote.
Yes.
And then another term in which I can just take the time order.
No, that's not a separate term. There's only one. You see, this term is decided by the fact that I pick the annihilation operator or this creation operator at minus infinity, this at minus infinity, this at plus infinity, this at plus infinity. It's not, there is not one more term here which has F2 to the right. Just look, so this is why I said you should look at this carefully. There's 16 terms here, but the 16 terms here are decided by, for the phi f3, did you pick the one at infinity or the one at minus infinity? For phi f4, did you pick the one at infinity or the one at minus infinity? For this, did you pick the one at infinity or minus infinity? Those are the 2-factor choices you have in all cases. Okay. You see, so okay. So this one is 0. Okay, let's look at another term. I won't show it for all terms. Okay, but the pattern should become clear. So give me another term we should look at. Which one? Tell me what I should write. Just tell me any term. There are 15 terms. Phi f1 at infinity. Okay, that one we got. And then maybe phi dagger f4. Like this, right? Good. But you see, this is also 0 for the same reason. Right, and so this one you can pick phi dagger f4 at infinity. Maybe you pick phi f2 at I don't know where you want to pick. Let's pick this at minus infinity, and let's pick phi f3 at I don't know. Okay. But this is also 0 for the same reason, because this is an annihilation operator, right? Which is so it's a creation operator. The creation operator acts in the vacuum from the left; it gives you 0. Okay. Now, it was here you might have been a little worried about the order of limits. For instance, let's say I put phi f4 a dagger at infinity first. Let me write this way. I could have written this term this way. However, because these operators at infinity, because notice here, because f1 is orthogonal to f4, I can commute these operators at infinity. Okay? So phi f4 dagger at infinity, with a phi f1 doesn't give you any, it has to give you 0. Okay. You see that? You see the assumption of why f1 and f4 are orthogonal is important here. Because otherwise this could have given you some term. It doesn't give you any term because f1 can move to the left. Okay? So you see, we can keep playing this game, but this, it's pretty obvious that the only term that will contribute is one where you pick up, the creation operators at minus infinity and the annihilation operators at plus infinity. If you try to do anything else, you'll get 0. Okay. Okay, so that proves, in fact, this is in fact the result that we started with, this result. Right? And so that proves the formula that we have on the board here. You can persuade yourself that all the other 14 terms that we did, or 13 terms we didn't consider 0, but is it clear why every other term is 0? Okay, good. So, huh?
We used to take different combinations of conjections, so we get 2 or 3 diagrams for any process.
We might get many diagrams for the process. There's no, we didn't say any, there's no diagrams here. Yes, there might be many diagrams, or there might be many more than 3 diagrams. There might be hundreds of diagrams if you go to higher loops. This is a non-perturbative statement. This is not a statement about diagrams or perturbation theory or anything. But what's the question? But go on.
I think like there is only one term, only one diagram.
No. This term has nothing to do with diagrams. There are no diagrams here because this is not an interaction picture operator. This is a full Heisenberg picture operator. It's the field operator really taken to plus infinity. Okay. We are calling it a creation operator, but that's, remember, no, it acts like a creation operator only because you're taking the field and pushing it off to infinity. If you take the field and you integrate it with this f of x or these modes, and you push this off to infinity, then you get some operators which behave like creation annihilation operators, but those are only in the far future and the far past. Okay? So the S matrix is defined by saying we have free fields in the very far past. You take the field, integrate with wave packets which separate in the very far past. That creates some states. Similarly, you can define some states in the far future. And that's your Hilbert space. And then you look at the overlap between that. There is no statement about diagrams or about interaction picture. And this is not a contraction. There are no contractions here. We are certainly not using Wick's theorem because there's no H0, no HI, nothing. All of those things only make sense when we have H0 and HI. Everything we've done here is just some exact statement about fully interacting fields. So this is a formal result for the S matrix, which it certainly doesn't say there's one diagram. There could, in fact, when you compute the S matrix, you could have hundreds of diagrams or thousands of diagrams. There's no, this is not saying that there's only one diagram. So please be clear about the fact that this is really an exact statement about the S matrix. Okay. Are there other questions about this? Okay, there are other ways to derive this formula. If you open Peskin and Schroeder, you will find a different formula which will reach the same conclusion. And the other ways to derive the formula basically start with this definition that this is the S matrix where you took the points off to infinity, and then try and argue that by taking things off to infinity, you pick up only this pole, okay? And this contribution, the way it connects to everything, yeah. So they try and argue that by pushing these fields off to infinity, okay, you pick up a certain pole in the correlation function, and if you strip off that pole, you get back the S matrix. Okay? So the argument is basically that pushing these fields off to infinity looks like it creates the state, but also gives you this pole in the correlation function, and therefore stripping off the pole will give you back the S matrix. So that's roughly the way Peskin and Schroeder derive this. There are different derivations in the literature, but of course they all end up with the same answer. This derivation is kind of clean, I feel, but you can look at others. Okay, let me emphasize a very important thing about this. Okay. You see, I said this is related to what we just said, right? In this LSZ reduction formula, right, how do you define the field phi h? What is the field phi h that goes into defining the formula? And that's important because there is no good definition of which field you call the interacting field, right? Let's say somebody says, I want to use the field phi h plus phi squared by 2, or something else like that, right? Then that will give you a different set of interactions from the interactions that we have here. maybe if you had a FIFO theory and you redefine the field, you'll get some other interactions, not FIFO, but something else, okay? However, in principle, that's also a good definition. It's the same theory, written in some other variables. So, in fact, it's important that in deriving the LSZ reduction formula, we never actually said that phi was some kind of elementary field or the field that entered the Lagrangian or anything else, right? The LSZ reduction formula in fact, this formula also works with any operator So, if I give you some other operator Q, all I really want is that all I really want is that this operator Q, when I act with this Q of x, should give you e to the iq dot x, and you want that. Other than that, you can use any such operator Q in the LSZ reduction formula. Okay? Any such Q Why do you specify only the one particle matrix elements? Why don't we try to specify also the two particle matrix elements and so on for phi or for Q? That's right. The one particle matrix elements are unique, right? The two particle matrix elements are not specified even for the field phi. They depend on the theory, they depend on what we call the operator. And to say that we are looking at the two particle state Q1, Q2 is actually meaningless. It's meaningless because even here, the fact that there's a non-trivial S matrix tells you there are two particle states at least, right? There is the in Q1, Q2 and there's an out Q1, Q2, and those are not the same. Right? The state that you call Q1, Q2 in the in case is not the same as the state that you call Q1, Q2 in the out case. That's why there's an S matrix. Okay. So the S matrix tells you, so it's really one particle states which are special. One particle states are special because they are uniquely specified by their conserved charges. And provided this Q operator creates one particle states correctly, it gives you the correct S matrix in the LSZ reduction formula. Okay. So there's for instance, right, let's say you said you want to compute the proton S matrix, right? Or you want to right. The other point is that or let's say you want to compute some some S matrix of the hydrogen atom, for instance, okay, or the S matrix of some other bound state. Then you could have said, well, I don't quite have some field that describes. So let me give you a better example. So, for instance, we haven't studied quantum chromodynamics, but in quantum chromodynamics, right, we have these baryons. Okay? We have states which are bound states of quarks, okay? Or maybe we have some other bound states of quarks and gluons and so on, right? And we could say let's say we want to compute the S matrix of two of these bound states. Now you could say, well, those bound states are not elementary particles, right? They don't correspond to any elementary fields in the Lagrangian. But you can still compute the S matrix of those bound states because if those bound states are stable states, there is some operator that you need to write down that just has some overlap with the one particle states of those bound states. And then you put that in the LSZ reduction formula, and it will tell you what the S matrix of those bound states is. Of course, it might be very hard to actually do the perturbation theory and evaluate the LSZ reduction formula. But in principle, we don't have a problem in defining what the S matrix, even of bound states or states which don't appear as excitations of elementary fields is because of this property. Okay. So Okay, is it clear why? Because all you don't want anywhere that Q should be an elementary field operator. You just want something which has the right one particle matrix element. And that's why I put elementary in inverted commas, because in the general interacting theory, sometimes what you call elementary might depend. And in fact, in field theories, there are sometimes dualities that tell you one theory is the same as the other theory, where elementary fields in one are very different from elementary fields in the other. Huh. Huh. What? Why do we need what? What do you mean? Why do we need that? Yes. Yes. That's just when you might want to look at a particular regime of where the S matrix simplifies. So for instance, if you want to look at the fact that you have these protons are made up of quarks, right? You might want to look at a very high energy scattering, where the scattering element of these protons is dominated by some scattering element where the quarks really become free. So the fact that the S matrix has various properties at different energy scales is not in contradiction with this. This is just saying you can define the S matrix by doing this. This is not saying you can, when you said you can compute using LS, that doesn't, we've not computed anything. We've written an expression for the LS, for the S matrix, right? So the LSZ will say this is the expression you need to compute, but you still need to calculate, what this time ordered product is. That might be easier to calculate at some momenta or at some other momenta. In the case of QCD, it's easy to calculate when you're in very high energies, because QCD has a property of being asymptotically free. It's hard to calculate when you're at low energies, because there this theory runs to being strongly coupled. So there, it might be that sometimes you can compute this only in some regimes or some other regimes, but the definition of the S matrix is always good. So you shouldn't get confused between the fact that we can use, maybe I shouldn't write compute to define, write an expression for. I mean, compute doesn't mean that the LSZ is some magic thing which is going to do all calculations for you, right? It just means it'll tell you what is the expression you need to compute. It's not like this is some magic machine which is going to give you answers. But at least tells you what you should try to calculate. You still have to do the calculation.
So everything comes down to calculating.
It always comes down to calculating the correlation function. That's it. That's it. Yeah. But there's no problem in trying. Let's say you wanted to compute the S matrix of a hydrogen atom, or let's say you took an atom of electron and a positron, which is unstable. But say you try to take some bound state of those, and you try to compute the S matrix. You would have said, there's no elementary field, so how do you compute it? Well, you can still compute it as long as you think of some operator. Maybe it's one electron, one positron field, or one electron, one proton field, which creates, which has some overlap with one particle hydrogen atom states. And then you just put that in the LSZ formula. So now you might get an 8-point correlator instead of a 4-point correlator to compute a 4-point scattering, right? Because the Q you're using was in fact a product of two fields. Then you have to compute that, which you might or might not be able to compute. Okay, good. So that's what I wanted to say about LSZ. Are there any questions about this? Okay. So now I'm going to change gears, and so now we've kind of come to the end of all the formal techniques that we need to develop. So just to recap what we've been doing, we started with field theory, why field theory was necessary, and then we did our simple naive scattering theory, where we said we have some vacuum and we are not very careful about the vacuum, and we said we have some in and out states, we're not very careful about that, but we could still compute some physical processes. Okay? Now we've correctly defined the S matrix in terms of the physical vacuum and in terms of these correlators which are intrinsic to the theory. So the remainder of the course is now to actually try and compute more complicated processes, including processes at loop level and higher, where we need to worry about renormalization. Okay, so we are now going to try and use, and if we had not had this formalism and this careful understanding of what we need to compute, we would not have been able to proceed beyond where we have already, what we have already done, which is some tree-level processes. Okay, so I'm now going to shift gears and start talking about one-loop amplitudes and questions of renormalization. If there are any more questions about LSZ, you can ask them now. Otherwise, we'll shift to a different, very different discussion. Okay. Huh. 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 Hmm.
So what you said is it doesn't work beyond 3 levels. That is because we have all those loop diagrams.
In one, yeah, that's for example one reason for that. But that would not even, if you wanted to compute, for instance, that's one thing which is wrong. But in that formalism, if you wanted to ask, how do you compute the scattering between some of these bound states, for instance, there's not even a good way to frame it. Okay. You would worry if you try to compute at higher order in that as to what, yeah. How you're defining your in and out states, right? So you would worry about, I mean, there are many things that would start to go wrong. The disconnected diagrams being one, the inability to compute, define the S matrix more generally being another. So you would, there are many things that would go wrong if you started to do that.
Exactly. What are we doing wrong?
Well, what would you try to compute if you wanted to compute at higher order? Like, what is the quantity that you're going to compute? So, what we had not even clearly defined what it is we were going to compute, right? We were saying we define some K1, K2, and we define something else which is K3, K4, and we assume, we compute some S matrix element between them. But really, we were not even clear about what this K1, K2 were. We were assuming there was some notion of K1, K2, which was defined in the free particle Hilbert space. Okay. But as you see here, what we really need to talk about is, there are different notions of multi-particle states, one in the far past, one in the far future, and we want to look at the overlap between that. Now, what we were doing there was we were saying, well, we want to take one state which is K1, K2, defined in the far past, evolve that to the far future using the interaction picture, and define K1, K2 in the far future to be the evolved thing of this perturbative state. So we could do that, but it's not clear, that's something that's I mean, let me say it another way. Everything we do from here will start with this formula. We'll start with saying, there's a Green's function we need to compute and amputate things and so on. In the absence of this clear definition, we would not be clear about what we are computing. So let me say it more practically. The disconnected diagrams is one. The other practical problem that would arise is you will find when we do this, when we do one loop diagrams, there's a factor you will get, which is sometimes written as part of the LSZ reduction formula, which is called wave function renormalization factor. Okay. This wave function, we've not written that factor because we've normalized the field in this way. Okay. In the formalism that we were doing, it would not be clear how to deal with those factors that arise, or how to renormalize the field at higher than one loop, at higher than tree level order. Okay. So from a practical perspective, there are at least two things that you already see would go wrong. One of them is the disconnected diagrams. The other is the fact that you wouldn't know how to normalize the field, so you wouldn't know how to normalize the external states. You can say that was really the problem in that, right? We hadn't defined the external states carefully, and so indeed you will see that when we do this wave function renormalization, what we'll do is we'll have to change the definition of the field so as to get this right. Or alternately, you can allow this to vary with some factor z, but then you have to strip off those factors z in the LSZ reduction formula. And those terms you would not get correctly in this naive perturbation theory. You would also not get these bound state scattering elements and other definitions of the S matrix more formally, although we won't do it in this course, so you might say that that's something which doesn't matter, but you would not have, in general, you would not be able to define the S matrix using that naive picture.
Disconnected diagram anyway doesn't contribute.
Yeah, but they don't contribute because we did something careful, right? I mean, maybe we could make lots of mistakes and get the right answer that way, but that's not the way we want to go, right? It's true, we could kind of work with that thing, and we could say, well, I forgot to include the disconnected diagrams, and then maybe we accidentally normalize the field correctly and so on. So it's true that you could do the old thing and make a lot of mistakes, or kind of stumble on the right answer, but that's presumably not what we want to do.
So I was just thinking about
Yeah.
like to try to pinpoint like exactly why do we have disconnected diagrams of the other components, but here they just cancel out.
Well, no, it's clear why we have them. We have them because we didn't choose the vacuum correctly. It's always about the external states and the vacuum. That's what we are not careful about in the other formulas. And so it's wave function renormalization disconnected diagrams. Okay. Okay, good. So today I don't want to say because we are starting. I just want to introduce you, to where we start to get infinities and say a little bit about how we want to think about this, and then we'll start doing more concrete things from next time. So in this discussion of one loop amplitudes, which we'll do for some time, I'll discuss both the phi to the 4 theory and this other case. This is what Coleman calls model 3, and this is what this is the phi to the 4 theory. The phi to the 4 theory has some advantages. This has some advantages. You can use both of them to illustrate different aspects of one loop amplitude. So we'll discuss both. Yeah. So let's first look at okay. So let's consider the same 2 to 2 scattering process that we have earlier considered at one loop, and let's ask what happens if you take the phi to the 4 theory and do the process but to next order and perturbation theory. Okay. So what we are instructed to compute in this is the 4-point correlation function, right? To compute the 2 to 2 S matrix element. So we'll compute the 4-point correlation function. As I said, the answer will be much the same as what we had previously. There'll be some propagators that will be sitting externally. There's some wave function renormalization factors. We don't have to worry about them for now. But here's one diagram, for instance, that you would get. Okay, which is, let me make all the momenta incoming. There are 2 other diagrams that you get to this process. Okay, but this is one diagram that contributes to 2 to 2 scattering. Okay. So there's one diagram which is this one, and there's this one, and there are plus 2 others, which are called, this is called the S channel diagram. Sometimes those are called the T and the U channel diagram, but we'll see them in a minute. Okay, this diagram we already evaluated, right? It told us what the scattering amplitude was at tree level. It was just minus I lambda. Okay. Now there's this diagram, and let's try and ask how this diagram behaves. And you see, what's happening is the following. Right? What's happening is we have, let's just use our Feynman rules to write down the value of this diagram. We'll do this more systematically. Right? We have a minus I lambda coming from vertex 1. Okay, this. So coming from here, it's coming from here. Then there's a propagator. Okay. Notice that there's something which is unusual in what we have now, okay, which was not the case in what we did at tree level. And what's unusual is the following. This momentum we can mark as P, okay, but this momentum is not now fixed by energy conservation. Okay. In these tree diagrams, whenever we had exchange momenta, they were always completely fixed by imposing energy momentum conservation at the vertex. However, here we find that this momentum, if you call this momentum P, okay, then this momentum is not fixed by energy momentum conservation. Instead, this side you get P plus K3 plus K4. Okay. There is an overall energy momentum conserving delta function which tells you that K1 plus K2 plus K3 plus K4 is 0. But if you call this P, this is P plus K3 plus K4, and you can't fix what the value of P is. There's no unique value of P that will satisfy energy momentum conservation. Okay. So you get a propagator which looks like P squared minus M squared plus I epsilon. The epsilon will turn out to be very important now. You get another propagator which looks like P plus K3 plus K4 squared minus M squared plus I epsilon. Okay. And because you can't fix P, just the Feynman rules of following the Wick's theorem will tell you need to integrate overall D4P. Okay. Okay. Now, we'll evaluate this integral later in a more systematic way. However, what I want to point out right now is just that, this is actually a Lorentzian integral. So to evaluate it, we'll have to go to, Euclidean space and rotate the integral and so on. However, what I want to point out right now is simply the fact that, this integral looks like D4P, but what you have in the denominator is also P to the power 4. Okay. So this is a log divergent integral. And this is, a standard phenomena that occurs in quantum field theory, which is that, when you start computing processes beyond tree level, beyond the most elementary order, you find that quantum fluctuations cause these infinities to appear, as you see here. Okay. So is it clear why you get this diagram and why this is also a logarithmically divergent diagram? Okay. Okay. So before we discuss a little bit about, how you deal with these in a practical sense, I want to say, it's important to understand where these divergences are arising from. Okay. You see, imagine that we have some. So I want to say a little bit about philosophy, and philosophy is kind of important to understand because it's important to kind of realize that these are not some very mysterious properties of the theory, but in a sense, if you thought about it correctly, we should have realized that such effects would occur. Okay. So the point is that, imagine this is some field theory that we've written down, which is some phi to the 4th theory, right? But in the end, this phi to the 4th theory is describing some physical system, which might have some, ultimate description in terms of, some discrete system or something else, right? So it might have some ultimate UV complete, description at the microscopic scale. Okay. So we think of this field theory is an effective field theory. All the field theories we deal with, we should always think of them as effective field theory. With some UV complete microscopic description. And this is something which is pretty important to understand. Whenever you think of some field theory, including our standard model, and maybe this eventually, this kind of philosophy came from condensed matter, but was also very useful in particle physics. We think of the field theories that we are seeing and we are dealing with, not as some deep or ultimate descriptions of the world, but really some low energy description of some more fundamental reality that we don't have access to directly. So for example, there is some description of atoms in this table, and there's some description you can write down. However, if you just hit the table, then you can describe the excitations of the table in terms of some excitations of some low energy phonons, and you might be able to write down some field theory for that. And this is something that we see all the time, right? Whenever we have waves, you have the ocean, you want to write down some description of the waves of the ocean. You don't really have to care about what's happening to the intermolecular forces between the hydrogen atoms. There are some effective sets of parameters that you can use to describe the propagation of large long distance physics of these oceanic waves. Okay. And that's the philosophy that we take here. Okay. How is that important to what I just said about infinities? The point is that at long distances, okay, the microscopic parameters combine to give us some physical observables. Okay. And the effective field theory that we have, okay, is something that relates one set of physical observables to another set of physical observables. Okay. If we try to relate the physical observables that we have to the directly to the microscopic parameters, we might find that that relationship is very complicated. If I try to say, well, there's some material property of this system, okay, and I try to directly relate that material property, maybe the wave velocity that you have here, to what is happening to the intermolecular forces, I might find that there is some very complicated relationship. And because the scales at which I'm looking at physics is very different from the scales that you have at the intermolecular level, you might well find that there are terms which look like they're blowing up or they're diverging in that relationship. Okay? That is a sign often that you're asking the wrong physical questions. Okay? So this infinity we now think of as arising, okay? These infinities, they arise if we are not careful about relating physical observables by that I mean, if you're not careful about relating one set of physical observables to another set of physical observables. Rather, if we try and ask questions directly in terms of some microscopic parameters of the theory, we will find that we get these complicated relationships, and that is how we eventually now understand these infinities. Okay, so in this case, what is happening? In this case, what's happening is we've written down some field theory, right? And we've not been careful about what the limits of the validity of this field theory are. Okay? So imagine that I write down some lattice field theory, and this is actually how we do calculations. Imagine that I discretize space-time and I put a field phi at every point in space. And then I say, there's some interaction between these phi's, and the interaction is given by this lambda phi to the 4 by 4 factorial, okay, between these fields phi's which are defined as the lattice points. Okay. However, this value of lambda that I'm putting in is really, from this perspective, a microscopic parameter of the theory, because it's telling me how my microscopic fields which live on the different lattice points are interacting with each other. Okay. What I want to measure at long distance is not this microscopic lambda. Right? What I want to measure at long distance is some other notion of lambda. For instance, I might say I want to look at 2 to 2 scattering and say that that 2 to 2 scattering amplitude is my definition, my operational definition of what I want to call lambda at some energy. And then I might want to say, how is 2 to 2 scattering at one energy related to 2 to 2 scattering at another energy? If you ask the right physical questions, then we'll find that these kinds of infinities will go away. Okay. However, if you ask the wrong kinds of physical questions, if you ask questions about how the parameters that we are looking at, how experiments are related to the microscopic parameters of the theory, then you'll often find that there's these infinities, and that comes from thinking of the field theory as an effective field theory that's related to some ultimate more microscopic description, and realizing that when you do that, you should always what we expect is just that the microscopic parameters will give us some effective parameters, and if you ask questions about how those effective parameters are related to one another, you expect to get sensible answers. Okay. Okay, let me however say a little bit more about if you open the old literature on quantum field theory, you will find a lot of discussion of what are called renormalizable field theories and non-renormalizable field theories and so on. And let me just frame that also in this microscopic language, right? Yeah.
Instead of taking this approach of just look at that is why do we have
What do you mean? Why do you have an energy scale? you define the theory. Let's say you imagine you define the theory on a lattice. You do quantum mechanics in a lattice. You can do that quantum mechanics. You can define some lambda, and you'll get some answers. But what you'll find is that if you work directly in terms of parameters defined in the lattice scale is just appearing all over the place. So it's appearing all over the place, right? The question is there some meaningful long distance physics that you can get that doesn't make reference to a lattice scale? And in this case, it turns out there is, right? So when you have a well-defined field theory, the answer is there is some meaningful thing in which you can reabsorb the lattice scale and relate one set of low energy experiments to another set of low energy experiments.
But why do we necessarily have to think as far as the mathematics is concerned?
This is a mathematical statement that you try to define. So let's say you want to define the theory, right? So the question is, you define the theory in terms of, so let's say you have to define the theory and you have an infinite number of degrees of freedom. So to define the theory, you have to think of some regularization first. So you define the theory in a lattice regularization, you'll get some answer. In that answer, the lattice scale will appear all over the place. Okay? This is a perfectly mathematical statement. Now the question is, can you ask some physics? So that's just some answer that you get for the theory. Right? Now the question is, what is the physics that you can extract from that? And the physics is that you have to realize that the lattice scale is not really fundamental. It's and at low energies you see you don't directly measure the lattice scale. What you measure is some combination of these parameters, and that combination of parameters gives you an effective field theory. So this is it's a mathematical statement as well.
I don't understand why the discretization comes in.
But how would you define the theory otherwise? Continua or continuums or infinities are always defined, even by the way, when you define mathematically real numbers, always defined by starting with a discrete set and taking things to infinity.
So there is by default a discrete link. So
That's the only way. That's the only way we know of defining a continuum theory is starting with a discrete set and then taking some limits where you take the scales to infinity. The question is, when you take those limits, how do you take those limits, right? And if at every stage you say, I'm going to ask, how is my low energy physics related to some microscopic physics, then of course, you expect the lattice scale will show up everywhere there.
Fundamentally, you're assuming it not to be.
Well, actually, what does continuous even mean, right? Continuous is not a well-defined thing. The only way we understand continuous actually is by thinking, and the thing is that there's also, well, since you're asking a mathematical question, I'm asking you mathematically what continuous means. And in fact, mathematically, continuous always means you start with discrete and try and take the limit. Okay, that's how continuums are defined. But from a physical point of view, we certainly don't know that the theory we have is really valid all the way up to infinite scales, right? So from a physical point of view, it's a very reasonable thing. And surely, the physical answers that you have shouldn't depend on what's happening deep in the UV. It shouldn't depend on the world around us. Might well be a discrete, world. No. Lattice scale is not unique for the theory, right? The lattice scale is some definition we're using. In the end, we want to take, the lattice is like a cutoff, but in the end, we don't want to say anything that depends on the lattice scale. Right? So we don't want to say, well, somebody defined the lambda 4 theory. Their computer was a very big computer, so they used 100,000 lattice points. Somebody, had an even bigger computer. They used 1 million lattice points. As long as you have as long as you have enough number of lattice points, you expect that the low energy physics doesn't really care about those microscopic parameters, right? So if you ask the right physical questions with the right physical observables, which relate one set of physics, then you don't expect any dependence on this regularization that you're using. Okay. Let me say something though a little bit more physical, which is the following, right? It's important. Well, okay, maybe not. Let me not try and say this now. I'll say this next time about different kinds of parameters. I wanted to say something about relevant, marginal, and irrelevant parameters, but I have only a few minutes, so let me not say it this time. I'll say it next time because that's an important concept. Let me just summarize what I was trying to say. Okay. What I was trying to say was that if you start with quantum field theories and you start computing processes beyond leading order, you will immediately find that you run into infinities. The way you should understand these infinities is that you're trying to ask the wrong question. If you ask the right question, which relates one set of low energy physical observables to another set of low energy physical observables, as opposed to trying to ask a question which relates low energy observables to microscopic parameters, you will find that these infinities do not appear if your theory is some non-trivial theory. It might of course happen that there is no way to relate physical questions. Some things are just genuinely UV sensitive. They're really sensitive to the microscopic parameters. And when you do that, then you say that, well, we can't answer these questions because there genuinely is a sensitivity to what is happening at the UV scale. Okay? But if your field theory makes sense, if you have a good description of the world, then you expect that the UV physics should not enter into your low energy description of how the world works, which is not UV divergent. In general, in quantum field theories, in any theory, you will always find that there's some amount of renormalization you need to do. There are these theories, for instance, called conformal field theories, okay? Where in some of these questions you find that if you ask some kinds of questions, you'll find that you don't have UV divergences. But even there, if you ask other kinds of questions, you will find you have UV divergences, because in quantum field theory, you always have to be careful about how you define operators, how you define things. So you'll hear this, we've discussed a few times conformal field theories. In these conformal field theories, you'll find that some of these UV divergences don't appear. But for other kinds of questions, there are still UV divergences. And there, once again, the point is that if you ask the right kinds of questions, then you don't have UV divergences. So UV divergences are always a sign of asking the wrong physical question. So to say that there are some theories in which the UV divergences, some theories are not, is kind of not the right way to phrase things. Because even if you take a very good, nice, well-defined theory and you ask the wrong question there, you'll get a UV divergence. Okay.
Our results are scale dependent, then we'll never know. Then we'll never know that in microscopic scale there is some.
The issue of scale dependence is a more physical thing, which I'll explain next time. But the issue of how some answers depend with scale, that's a physical question. You can ask, I'm scattering two particles of each other. How does that scattering, does the strength of the scattering increase with energy or does it decrease with energy? That's a physical question. In these conformal field theories, things look the same at different energy scales. That's different from this question of UV divergences. UV divergences are just because, you didn't set up your question correctly. If you set up the question correctly, then you'll find that, the UV divergences go away. The scale dependence might remain. That's a physical aspect of the theory. Or it might go away. But that's a physical aspect of the theory. Okay, let me stop here and we'll come back next time to discuss this.